we have a scalar field phi. It's d-dimensional in real space, and it transforms under the symmetry loop GF. And using this field phi, we construct the most general potential of order P. I call it Vp. And Vp is summation of C alpha, I alpha. C alpha are the coefficients and I alpha are the invariants up to this order P. And we assume that up to this order, there are n independent invariants. So the summation is from 1 to n. A point to note here is that once we have the potential Vp, if you look at its symmetry group, it can be larger than the original group GF. So I call this symmetry group of the potential as GFP. These extra symmetries that arise are sometimes called accidental symmetries by authors. Throughout my discussion, when I talk about the symmetry group of the potential, I am referring to this group GFP. So once we have the potential, we can look for stationary points. Stationary points are where the first derivatives vanish. For our purpose, let us for the moment just concentrate on one particular stationary point and see how it changes when you change the coefficients. So basically you have a map from the space of the coefficients to the space of the field. So that is shown here as this definition. And you can see that the domain of the map, I've shown it with the letter capital C. And what is it? It is an open subset of Rn, because we have n real coefficients. And throughout this space, we may not be able to meaningfully define this map. So we have to get the open subset of this n-dimensional space where we define this map. And that domain is C. And of course, the map is pointing to the space of the field, which is d-dimensional, so Rd. So as I said before, stationary points always appear in orbits. So if you have a stationary point phi 0c, then it automatically implies that you have stationary points g of phi 0c for all g element of GFP, which is GFP is the symmetry group of the potential. Now I make this statement. Consider a set of coefficients c and let phi 0c be the corresponding stationary point. If HFP is the stabilizer of this particular stationary point, then for all phi 0c, with c being any element of the domain C, HFP will still be the stationary point. This results in intrinsic constraints of the form h minus I phi 0c equal to 0 for all h element of HFP, where I is the identity. Now, I am not giving the proof of these statements. For that, you may please go through the paper. Basically, what these statements show is that stabilizers of stationary points always lead to intrinsic constraints. This statement explains what happened in the previous video. We started with a red point in the x-axis, and we saw that when you change the coefficients, the point moved only along the x-axis, because for a point in the x-axis we have a Z2 stabilizer, and that Z2 stabilizer generates an intrinsic constraint, and that forces the point to move along the axis only. And the same is true with the point along 2π/3 and so on. Now I ask this question: can the symmetry group of a set of stationary points be larger than the symmetry group of the potential itself? So to answer this, I first define a group which I call G tilde FP. So this group is the largest group such that given phi 0 C stationary point, we have a set of stationary points G of phi 0 C with G element of this group G tilde FP. And this should be true for all coefficients within the domain. So this should be independent of the coefficients. You can clearly see that for G element of this GFP, the symmetry group of the potential, this equation remains valid. So the question is this group, can this group G tilde FP be larger than GFP? So to answer that question, we go back to our potential Vp, which we wrote as a summation. Now I rewrite it in a slightly different form. Here I write it as two summations. The first summation is from 1 to small n, and we have the coefficients C alpha and the invariance I alpha. The rest of the terms are in the second summation, which goes from alpha equal to n plus 1 to capital N. And we have the coefficient C alpha, and then we have x transpose y. And what are these x and y? X and y are multiplets of the group GFP, which transforms under some representation. Both of them are transforming under the same representation. Therefore, x transpose y, this is like a dot product. This quantity will be an invariant. So this is just writing the invariant in a slightly different form, that's all. Once I write that, I make three assumptions. So the first assumption is, we consider the first summation, and this first summation is assumed to be invariant under the larger group G tilde FP. So these terms I alpha are invariant not only under GFP but also under the larger group G tilde FP. Now the second assumption. So we have the terms x and y. They are multiplets of different representations of G tilde FP. So I already said that they are multiplets of the same representation under EFP. What I am saying here is that under G tilde FP also they are multiplets, but they are multiplets under different representations. So basically, when you look at the quantity x transpose y, it will not be invariant under G tilde FP. And the third assumption. So before going to the assumption, I have to make certain definitions. So you already know that C is the domain of our map phi 0 C. So in this domain, I'm going to impose certain constraints. Constraints are the coefficients of the second summation, that is C alpha with alpha ranging from n plus 1 to capital N. So those coefficients, I'm going to impose a constraint that all of those coefficients are 0. So if you impose this constraint on our domain C, we obtain a lower dimensional space, and that space I call it Cn. So it's an n-dimensional, small n-dimensional space. And the restriction of our map phi 0c to this lower dimensional space, I'm going to call it phi 0cn. So the third assumption is that both x alpha and y alpha, with phi being equal to phi 0c in the restricted space, both of them vanish for all C element of this lower dimensional domain. So once we have these assumptions, let's see what happens. This equation is nothing but the definition of the stationary point. We have simply equated the first derivative of the potential to 0. And you can see that we have g of phi 0c as the stationary point for all g element of GFP. This is simply because stationary points form orbits. Now I have defined phi 0cn as the restriction of phi 0c to lower dimensional domain. So this statement should be valid for this restriction also. So we should be able to replace phi 0c with phi 0cn. I'll do that here. Phi 0c is replaced by phi 0cn. Now consider the third assumption. X and y vanishing throughout this restricted domain. So that means this derivative vanish throughout the domain. In other words, the first summation should be equal to 0. Now consider the first assumption. We are saying that this summation is invariant under the larger group G tilde FP. So that means here instead of GFP, we should be able to write G tilde FP. So I do that. Look at the second condition, second assumption. Second assumption says x alpha and y alpha are multiplets of different representations of G tilde FP. So since they vanish and since they are multiplets of G tilde FP, these terms should vanish for G element of G tilde FP also. That means I can include those terms and obtain this relationship. So what does this mean? What it means is that the potential has stationary points of the form G of phi 0cn for all G element of the larger group G tilde FP, even though the symmetry group of the potential is only GFP. X and Y, they vanish throughout our domain. So that means their coefficients, these C alpha with alpha ranging from n plus 1 to capital N, they don't play any role in determining the stationary points. Therefore, we obtain phi 0c without any restriction is equal to the restriction phi 0 Cn. The last set of n plus 1 to n set of coefficients doesn't appear in phi 0 C. And the full domain C is nothing but the lower dimensional domain Cn times R n minus n. So we can conclude that given a potential Vp, which is invariant under GFP, and given those three assumptions we made, we can see that we have stationary points g of phi 0 C for all g element of the larger group g tilde Fp, which is valid throughout our domain. This set of stationary points form an orbit under the larger group g tilde Fp. Since GFP, that is the symmetry group of the potential, is a subgroup of g tilde Fp, this orbit under g tilde Fp will be nothing but a union of several orbits under GFP. Just like GFP, g tilde Fp also generates intrinsic constraints. So there is a statement very similar to a previous statement I made. The statement is, we take some coefficient C in the domain and let phi 0 C be the stationary point. If H tilde Fp is the stabilizer of this phi 0 C under this larger group g tilde Fp, then for all phi 0 C, for all stationary points with C element of the whole domain, H tilde Fp will be the stabilizer. And this results in intrinsic constraints of the form H minus I times phi 0 C equal to 0 for all H element of stabilizer H tilde under the larger group G tilde. This completes our discussion about the origin of intrinsic constraints. Now over to part 4, where I use an example to demonstrate the concept that I have introduced in this video. At this moment, you may be wondering about those three assumptions that I made. Can situations exist where they appear spontaneously? The answer is yes. You will see that in the example.